What happens when you turn a fundamental theorem of number theory into a competitive battleground? Today, we are exploring a class of games where players manipulate piles of numbers according to the strict rules of the Fibonacci sequence. Let's first establish the ground rules, which rely on Zeckendorf's theorem. This theorem asserts that every positive integer acts as a unique sum of non-consecutive Fibonacci numbers, providing the target state for our game. To reach that unique state, players alternate turns using two specific local moves that mirror Fibonacci recurrence relations. You can either merge consecutive numbers into a larger one, or split duplicates into smaller and larger components. What makes this interesting is that despite the freedom of choice, the game never loops infinitely. Every move reduces a specific mathematical value called a monovariant, guaranteeing the game eventually ends at the Zeckendorf decomposition. Now that we understand the classical mechanics, let's look at how changing the rules of adjacency alters the strategy. The strategic landscape shifts dramatically depending on whether the pieces are ordered. In the classical unordered game, the second player usually wins, but if we align the pieces in a strict tuple, the advantage often flips to player 1. Beyond simple one-on-one matches, these games exhibit fascinating properties when we introduce randomness or extra players. For instance, if moves are chosen randomly rather than strategically, the distribution of game lengths begins to look like a standard bell curve. Zeckendorf-based games serve as a unique bridge connecting additive number theory with combinatorial game mechanics. They demonstrate how simple local rules can drive complex, predictable mathematical behaviors.